Okay, we're going to be using partial fractions a lot this chapter. So this video is just designed to review how partial fraction decompositions work. So some of you may not need to watch this at all if you're comfortable with your partial fraction decomposition, or if you're comfortable sort of catching up on the fly as we just go through the examples in the actual differential equations context. That's totally fine. But some of you might prefer to have more of a formal review, and so that's what this video is about. Okay, so I'm going to start with the linear factor rule. So given a proper rational function, that just means the degree on the top is strictly smaller than the degree on the bottom. It's kind of like with regular fractions, like 1/2, that's a proper function. Proper fraction, rather. 3/2, that would be an improper fraction because the number on top is bigger than the number on bottom. Okay? With rational functions, instead of looking at the value on the top, we look at the degree on the top. I'll just point out that 2/2, where the number on top is the same as the number on bottom, is also considered an improper fraction. To be proper, the number on top has to be strictly smaller. So for a proper rational function, the degree on top has to be strictly smaller than the degree on bottom. Now, nice thing about Laplace transforms is we're pretty much going to get proper rational functions. If we didn't have that, we could always just divide to get a polynomial plus a proper rational function. So just like here, 3/2, I could say, let's do 3 divided by 2. That goes in once. Oh, that would be 1.5. I can do the same thing basically with rational functions. Okay. We're not really going to need to do that in the context of differential equations, but that's what you would do if you had an improper rational function. Okay, so we're going to factor the denominator completely and combine like factors. Now, what I mean by that is that if I had something like 2x over x plus 1 times x plus 1 times x minus 1, that's completely factored, but I would just rewrite that as x plus 1 squared times x minus 1. So I would sort of consolidate if I had multiple copies of the same factor. Okay, so then every factor of this form, ax plus b, that's just an arbitrary linear function. Here it was x plus 1. I could have 2x plus 5. Okay, a linear function to a power. K, of course, is going to be a positive integer here. Okay, but for every factor of that form, that's going to contribute k fractions to the partial fraction decomposition. So this is actually k factors of ax plus b. The number of factors that I have determines the number of fractions that I'm going to get. And the rule for linear factors is that the denominators, we start with just the linear function. If it's repeated, the next fraction would have that linear function squared. If it's repeated 3 times, I'd have another fraction with that linear function cubed. If it was repeated 50 times, I would have 50 fractions, and the last one would have that linear function to the 50th power. Okay, so the denominators are just those that linear function, starting with the first power all the way up to the highest power that occurs. Okay. The numerators are all just constants. So these capital A's, I've got the first constant, the second constant, the third constant, they're all just constants. Now, we're going to have rules in a moment for what if we have an irreducible quadratic factor. So that's a quadratic that doesn't factor. A lot of times people want to view that and say, oh, that's a quadratic. But that's not an irreducible quadratic. That's a power of a linear. And so the numerator is just a constant. Okay, so let's just take a look at the general form that I would get for something like this. So if I had 2x over x plus 1 squared times x minus 1, I know that would break down into, well, let's see, x plus 1 occurs twice, so I'd have one fraction with an x plus 1 and one fraction with an x plus 1 squared. And then x minus 1 only occurs once, so I'd have one fraction with an x minus 1. Notice a total of 3 factors here, 1, 2, 3 fractions. Everything in the denominator is a linear or a power of a linear, so the numerators are just constants. I'm just going to call them A, B, and C. Okay. If I wanted to, I could call them A1, A2, and A3. Usually when I have just a few, I just start running through the alphabet. Okay. So that would be the general form of something like this. Okay. If I had 4x plus 2 over x cubed times x plus 1 squared times 3x minus 5. Okay. Notice that's a total of 6 factors. That's 1 copy of this, 2 of those, 3 of that. That's a total of 6 factors. So there are going to be 1, 2, 3, 4, 5, 6 fractions that we're going to have. 3 factors of x. So I'm going to have 1 denominator of x, 1 of x squared, and 1 of x cubed. 2 factors of x plus 1, so I'm going to have 1 denominator of x plus 1 and 1 denominator of x plus 1 squared. And then 1 factor of 3x minus 5, so I'll have that. All of these are linear or a power of a linear, so I just got A, B, C, D, E, F as the numbers, as the numerators of those fractions. They would just be constants. Okay. All right. Now, with one that's this long, I'm not going to go through solving for these constants. But let's take a look at this one and see if we can find what A, B, and C actually are. Okay, so what I'm going to do is I'm going to take this equation and I'm going to clear the denominators. So I'm going to multiply both sides by the least common denominator, and that's the least common denominator. That's essentially the rationale behind this. If I wanted to add up these fractions, I would find a common denominator, and that right there is the least common denominator. Sometimes people ask, why do I need x plus 1 squared? Why can't I just have another one with b over x plus 1? Well, if I did that, I could say, well, that's a plus b over x plus 1. That's really just one fraction. But notice, if I just had that, I wouldn't need to get this as my common denominator, because I'd have a common denominator of just x plus 1 times x minus 1. But this fraction doesn't reduce. Okay. So I do actually need all of these. Now, it will sometimes happen when you solve for the constants. You're allowed to solve for the constants and get 0. So in some particular cases, one of these fractions or more of them might actually drop out. But you gotta start with that. So if I multiply through by this LCD, what that's going to do here is just cancel everything. So I'll get 2x. So let me write it out. I'm multiplying by x plus 1 squared times x minus 1. So here I'm multiplying by x plus 1 squared times x minus 1. So when I distribute that to this, one of the x plus 1's will cancel, but the other one won't. So I'll have a times x plus 1 times x minus 1. Now when I distribute that to this, both x plus 1's will cancel. So I'll just have b times x minus 1. And when I distribute that to this, the x minus 1 will cancel, and I'll get c times x plus 1 squared. Okay. So I get this lovely equation. Notice a, b, and c are just unknown constants. So this is a quadratic equation. Yeah, because I've just got some x squareds. Okay. Now the original equation here was undefined if x was 1 or negative 1. But the numbers a, b, and c that make that equation true are going to make this equation true for all values of x. Because there's no way I can have a quadratic equation that's true everywhere except at 1 and negative 1. It's always defined, it's going to be true everywhere. So I basically have two techniques for finding a, b, and c. The first technique, which I'll write as option 1, is to plug in values for x. I need to find three numbers, a, b, and c. I'm going to need to plug in three numbers for x. Okay. The two that are the easiest to plug in are x equals 1 and x equals negative 1. So if I plug in x equals 1, this becomes 2. And that's going to equal, well, if I'm plugging in 1 for x, that kills off the a's. If I plug in 1 for x, that kills off the b's. This is going to give me c times 1 plus 1 is 2, squared is 4. So that tells me right there that c is equal to 1/2. Now, the other convenient number to plug in would be x equals negative 1. If I do that, the left-hand side becomes negative 2x. Now, if I plug in negative 1, that's going to kill off the a's. That's going to give me negative 2b. Okay. And that's going to kill off the c's. Okay. So, that's going to tell me that b is equal to 1. Okay. All right, now I'm out of really nice numbers to plug in because there's nothing else that's going to kill off any of these terms. But I still need to know what do I need to know? I know b and c. I need to know a. Okay, so I need a third value of x. Well, let's pick one. I've got infinitely many numbers to choose. I'm going to choose 0 because it's easy. Okay. So if I plug in 0 for x, the left-hand side becomes 0. The right-hand side, that becomes a times 1 times negative 1, so that's going to be negative a. Okay. Now this becomes negative 1 times b. I can use the fact that I actually already know what b is. So that's going to be, well, actually, let me write it out in general with the b's, but then I'll plug in. Okay. And if x is 0, this becomes 1 squared is 1, so plus c. But now that's 0 equals negative a. I know that b was 1, so minus 1. Oops. Plus c was 1/2. So 0, well, actually, I can add the a over. A is just negative 1 plus 1/2. A is negative 1/2. So that's one option, and this tends to work really nicely with linear factors, because with linear factors, there's a number you can plug in that makes that factor 0. So at least for these first two, they were super, super simple equations. Okay. Now I'm just going to write what we got. We got a was negative 1/2. We got b was 1, and we got c was positive 1/2. Okay. So that's option 1, plugging in values for x. That's usually what I go to when I've got linear factors. Although sometimes when I have repeated linear factors, I'll do that for the first two, and then I'll switch to option 2. So option 2 is to multiply out and equate like coefficients. So I've got 2x on the left side. This is going to be a times x squared minus 1 plus bx minus b plus c times x squared plus 2x plus 1. So I'm multiplying things out. Now I've still got to distribute the a here and the c here. So 2x is equal to ax squared minus a plus bx minus b plus cx squared plus 2cx plus c. And what I'm going to do now is I'm just going to combine like terms. So it looks like I've got 2x here. For the x squareds, I have a plus c of them. Now let's take a look at the x's. I've got 2cx plus bx, so that's going to be b plus 2c copies of x. And then if I look at my constant terms, I've got a negative a minus b plus c. So plus a minus a minus b plus c. Now, that's a polynomial in x. This is a polynomial in x. The only way two polynomials in x can be equal to each other is if the like coefficients are the same. So, I want to take a look at what powers of x do I actually have showing up. It looks like here I've got constants, x's, and x squareds. So, I'm going to look at just the number, which is the constant, the x's, and the x squareds. Now on the left-hand side, the constant that I have is 0. That's got to equal this, negative a minus b plus c. For the x's, I've got 2 of them on the left side. On the right side, I have b plus 2c. For the x squareds, I have none of them here, but I have a plus c of them here. So that gives me a system of 3 equations and 3 unknowns. It's just that none of them is quite as nice as what we had last time involving just one of the variables. But I can easily say here, well, a is just the opposite of c. Okay. So I can replace a with the opposite of c in this one. So I can get 0 is equal to the opposite of c, which would be c minus b plus c. So 0 is equal to negative b plus 2c. Then I've also got this equation that says that 2 is equal to b plus 2c. If I just add those equations, the b's are going to drop out. So 2 is equal to 4c. Okay, so c is equal to 1/2. Cool, that's what we got last time. A is the opposite of c, so that's the opposite of 1/2. That's what we got last time. Okay, and now I just need to find b. So let's see. I'm going to just use this equation. 2 is equal to b plus 2 times c would be 1/2. So that's 2 equals b plus 1. So b is going to equal 1. Okay. Now, I think it was a lot more work to do things this way. However, what I'll sometimes do is plug in particular values for x to get the first 2 values, and then once I already have 2 out of the 3 unknowns, or 4 out of the 5, whatever it might be, then I might multiply out and equate like coefficients to get the next one. We'll also see when we take a look at irreducible quadratic factors that sometimes this method is actually a little bit more straightforward in that context. So you can choose whichever method works best for you. I tend to go to plugging in numbers for x for linear factors, and I tend to multiply out and equate like coefficients for irreducible quadratics. Okay, so we will take a look at irreducible quadratics. We will do that in the next video.